Thank you everybody for attending and let's say for being interested in this area of work that is in a way could be seen as the past, but will be it deals with problems which will be with us for some time still. So we keep doing new topics on this, but for sure we have a wave of the project that started with the previous framework coming to an end, and let's say the first ones of the newer generation that start also producing results. So we have finished projects, we have running projects, and the philosophy has been to try and widen these kind of topics in the new work program are not always, I would say majority, not in the automotive platform. There is something, but it will be very targeted to zero emission vehicles. So the remaining emissions of zero emission vehicles. While in the new topics, you have to look for a specific area, which is impact on health of transport, which is wider. So it started mostly on automotive. You will see that we are broadening in some cases because many issues are common or similar, or we have lessons learned that can transfer from one to the other and so on. And this will go on also in the future. So for this, let's say, this year, we have mostly automotive, but let's say that there will be a kind of broadening, often in the same projects, the same project exactly to exploit these synergies. I'm happy to see the researchers that have been working on this in the projects we launched some time ago, covering in some cases things for the first time. There are some sort of underestimated or underrepresented areas that are covered. And I hope that we will be, let's say, learning on what they have found, what is really the latest in this area. So we have Tube, who worked on nanoparticles, let's say in particular. We have AeroSolfd, which is looking at retrofitting and let's say technologies that can deal with what is already in the fleet and in the market. And we know, as I said at the beginning, this will go on for some time. So in some cases, cities might appreciate to know that there are ways of reducing the emissions. Of course, with Euro 7 being less demanding, I think we launch it expecting something more than that, so to say. We have projects looking at secondary particles, which is an area that is one of those that I say a bit underappreciated. And then we have non-exhaust particles for tires. So we really, you see, a big variety. And that's, I think, what we'll need to do, as I say, in the future, looking at sectors which are also contributing to air quality issues, and sometimes a bit less regulated than automotive. And this is maybe one of the problems. So I would start with the first speaker, who is nPETS, looking at the PTWs, I think, right? I hope we will learn also something there. There's also noise, which is included in this area. By the way, I didn't mention that.
time for me.
Yeah, sorry, I I am finding the right.
Please use the microphone here because we have people listening to you online. So
Yeah.
if you want them to listen to you well, you should speak to the microphone.
Yeah, Mr. Ulf Olofsson from KTH will be introducing this to us. Thank you for being here.
Thank you. So I will present results from the nPETS project, nanoparticle emission from the transport sector. And as mentioned here, we are covering airports, harbors, train station, and roads. So we are trying to cover that. And we are looking down to the sub-100 nanometer particles. We are 7 universities running this project together. It's KTH, Stockholm University, Aerosols University, Thessaloniki, we have Karolinska Institute, University of Leeds, Tampere University, and Lund University. Together with 3 research institutes, that is CESIC, Institute Maronegri in Milan, and also CERT in Thessaloniki. And in addition, Barcelona and the city of Stockholm is working together with this, and finally one company, Brembo, that covers brake emissions. We set up this to be able to both measure the particles and also to cover the story of the particles from when they are created and transformed and until we inhale them or to reach us in other way. So we follow it from the source to the end. So we have improved quite a lot the knowledge of how different sources, both locations and also direct non-exhaust and exhaust sources, contribute to the sub-100 nanometer particle emissions. To do this, we must set up our own standards to actually use the same instruments at all places to be able to have comparable results, because there were no standards available when we started. So we have to define the rule of the game for ourselves regarding measuring on filters, sampling, counting the number of particles, and also generating systems to see the toxic effect. If we look at this, that we have taken from the down to 10 final review meeting and upgraded to our own story, we look at the emissions when they are fresh. So we have dedicated test environments where we run dynamometer tests to take brake emissions. We have used clutch test rigs to see clutch emissions. We have tested tire emissions, mostly studied tire emissions, since our sister project Leon T covers the other part, the non-studied tire versions. And we have also looked into the exhaust. In vehicle test, we have been looking at light vehicles. Our sister project ULTRHAS look at ship emissions. So we are covering a different part, and they are also covering the electric catenary for trains. We are covering the wheel rail contact. So we are mixing to get a database together, these 3 projects. What we then do is that we also look at what's happening at different locations. This is, for example, a road tunnel. So we have setups measuring in road tunnels, in street canyons, in harbors, in airports, to study and characterize the sub-100 nanometer particles. Then, as mentioned here, there are secondary particles. The particles change the chemistry, for instance, when there are sunlight on them. We have studied that both in street canyons, but also artificially in tribometers and in exhaust dynamometers for combustion engines. And finally, we have developed equipment and protocols so we can measure the toxic effect. We have used both filter test setups and air-liquid interfaces that directly exposure the emissions to human cells. No, wrong way. My tongue is a little bit slippery. So much of focus has been to develop systems that actually can give a tox score or give a risk analysis of the danger of the particles we inhale. To give a little bit of the overview of what we have done is that we have built two systems that has been turning around in Europe, air-liquid interface systems, where you can directly expose your cells to the emissions. So we are in situ testing, both in harbors, in roads, in railway tunnels, and at airports. And in parallel, use also sampling on filters to be able to compare the methods. We have set up all protocols for measuring these ultrafine particles, both how to sample and on filters and on airless systems. We have created a database where we have started to download the data for future open access. So far, we have found ultrafine particles at all places we have studied them, and at all places except one, they are above the WHO recommendation, their high limit. If we take away the urban background levels, but all places where we have transport influenced situation where people are visiting, we have ultrafine particles at levels that are above WHO recommendation levels. We have also seen that all non-exhaust sources contribute to ultrafine particles, both mechanical brakes, clutches, tire to road, when we are talking about studded tires, railway train to wheel to rail, and electric power system for trains all contribute to this. And also all exhaust sources contribute to ultrafine particle levels. That means that even if we run bioxygenated fuels, we also have ultrafine particle emissions. To give a bit of history, this is the ultrafine particle concentration in my hometown. That is data from 2001. And you can see the levels of the street canyon. That's the black line here, starting somewhere around plus 80,000 per cubic centimeters. We have the Euro 4, Euro 5, Euro 6 legislation, reducing, as I see it, the numbers. Sorry. And so we can see that but we are still well above the dashed line here. That is the WHO high level recommendation. We should be below this level if we follow the WHO recommendation. You can see the urban background that has decreased. So in urban background we are below the WHO regulation, and you can compare that with a long time measurement from the south of Sweden in a forest area where there are no traffic at all. The level we have with only natural sources. Still some work to do, but quite some achievements has been done. And as I said, all test sites in harbor, airports, street canyons has been above these WHO limits, except for one place. And that is a very confined space where we expected to have higher levels, and that is in underground railway platforms, where we actually had levels that were comparable to the urban background levels. So if you look at this graph, you see number concentrations of 4 to 5,000 for urban background and subway, summer and winter conditions. And you can and the WHO limit is 10,000. You can compare that to what we see in a road tunnel, 50 to 80,000. What we have spent some time is to exposure test. Okay, we can measure numbers, but we want to have a risk analysis also. How dangerous are these numbers? So start to make statement on that. So here we are measuring in a road tunnel, and you see the wall here, and next to that wall we have the OLE instrument. So the red hat here, that is the inlet of the air liquid interface exposure system, and below here we have the cells that are exposed to the emissions from the road tunnel. We have done that in our dedicated lab sampling and also in subways, like this. Based on the measurements we have done, we have also created emission factors, and we have also used already published emission factors, but we have created emission factors for clutches, for mechanical brakes. We have gathered data for ship emissions, for airport emissions, and starting to model the ultrafine particle concentration in the cities we are working with, that is Stockholm and Barcelona. And here is one example where I show the annual average particle number concentration for road traffic just using exhaust emissions. And then we have added the contribution for clutches, for brakes, for ship emissions. We have an harbor here, and we have an airport a little bit north of here to increase the modeling. The next step is that we use the data from the air liquid interface studies and the filter testing and also zebrafish testing to generate the risk of these emissions from different sources. And here is one example of what we are working with. This is ongoing work, I would say. This is where we are at the moment, but this is one example. Here we are following a paper by Park et al. Published in Scientific Reports previously, where we are actually giving each site a score in categories 1 to 4 for cytotoxicity, inflammation, and DNA damage, to be able to add this to the simulation of the city, to also give a risk score of being at that place. The challenge here is, as you can all understand, is to create a mean value out of all these factors, or out of this there. So that is one, and you can see we have different categories, we have different size for, and different effects of both, if we look at particles on the nano size and on the micro size, both for road and for subway particles, and also on individual components. That we can see that, for instance, the third rail gives another result than the ordinary rail. The third rail in a subway, that is where you get the electric power. So what do we expect how to use these results in the future? We believe that this limit that has been proposed by WHO will be hard to reach for cities. We have to struggle hard to go down to below 10,000 particles per cubic centimeters for sure. What we would like to add is the potential of using toxicity scoring to give a risk analysis to these numbers. So the effect of having 10,000 plus ultrafine particles in a harbor can be quite different to a street canyon or close to an airport. And that is where we want to set a statement currently. In the same manner, when we look at different components, we can use this kind of techniques for both exhaust and non-exhaust sources to give a risk analysis of different fuels or wearing materials. Yes? Time? Okay, 1 minute. So what we would like to do is to use this to, if we allow us to change the European market pad materials from low metallic to US market neo, we can significantly reduce the emissions, both in particle number and mass. That is an easy step to do if we don't have highway speed, outbound speed allowance, but we don't know the chemistry of these particles. So we need to continue to check. We will change the chemistry of what we inhale, and then we need also to just not see that we reduce the numbers. We need to see that we are not more toxic in these effects. So we see the impact pathway that we have emissions from transport sources. We have characterized them together with our sister projects and also from other sources. We are modeling the population exposure based on these measurement and emission factors we have generated in these all three projects, nPETS, Leon T and ULTRHAS. And we have started to create toxic score effects, and that after that we can have a socioeconomic aspect of policies generated to see the effect of future legislation. So, thank you.
For the questions, we would split between any immediate clarification, quick ones, and later at the end of all the session, instead something, let's say, more discussion. So if there are specific questions on the presentation itself, we do them now, otherwise we...
Yeah. Maybe just a quick one. I was intrigued by your slide that showed emissions, particle emissions in road tunnels in the summer was higher than in the winter in the tunnels and not for the other roads. I just wondered why.
That's a correct result. The winter, this is winter for road tunnel, this is summer for road tunnel. We have more particles in winter.
But why not in the...
Well, urban background,
okay, sorry.
this is urban background, so this is on an urban level in Stockholm. And here you have the subway, summer and winter time. We close the ventilation shafts, so there are no communication with the outside in the same way during the winter, so we have less emission going down from the street level, I would say. So the difference here is the part that is dragged down by the ventilation shafts with the subway system.
Thank you for your presentation. A quick question, how do you measure the dose in your RE system?
Exactly how we count the number of particles before and after, and then we have an effective density estimated at the place also. So that is of course an approximation, the effective density. The better we can estimate that, the better the dose we have. Yeah.
I would have one question myself. I was a bit intrigued by the result on the metro. I've seen results in other places where, at least in mass, it looked much worse.
Yes.
Is that because, I mean, have you done comparison with other metros? Is it maybe, for instance, that is better filtered, or it's that at nano level it's better than...
The answer to that is that it's much better at nano level. If you look at PM10, this is at least 10 times worse than the street level.
Okay, so it's more a mass effect than...
Yes, and we don't have so much sources for ultrafine particle generation.
Okay.
Because trains have if the trains have an effective regenerative braking system that modern trains have, then they create very little ultrafine particles. You need to reach a certain temperature to reach that, and they have designed the train so they don't reach that during the braking.
Thank you. Okay, so thank you for the presentation and the answers. And we move now to one of the projects with which you are filling up this database, which is, I think, a very important and lasting consequence of this project, which is Leon T looking at particle and noise emissions from tires, and presenting is Juan Garcia from IDIADA. The floor is yours.
Thank you, Mr. Chairman. Good afternoon, everybody, ladies and gentlemen. My name is Juan Garcia. I work for IDIADA Automotive Technology in Spain. I am the coordinator of the project LEONT. LEONT stands for Low Particle Emissions and Low Noise Tires. And as you know, tires are not very glamorous components, but they are extremely important in vehicles, as you know. They provide safety, they provide comfort, but they produce nowadays, as you all know, noise, the polluted environment, and particles. So these two issues, noise and particles, are mainly the concern of this project that tries to understand in a very transversal way how tires produce particularly particles, how they transmit their fate, how they disseminate into the environment, and how they affect people, and particularly health. Similarly, we are also working on noise issues, and so for some tires still that have some noise problems, like truck tires, that have a relatively high level of noise generation, and they somehow affect the noise, the sleep quality of people living around motorways. And so we are trying to find the impact of this sleep perturbation into cardiovascular effects potentially can be generated. So this project has basically these objectives, which basically are a breakdown of trying to explore and increase the knowledge and evidence about particle and noise emissions from tires and their associated effect on public health in order to propose mitigating measures through regulation, labeling, and design. And for that, of course, the three initial points cover the main issue, is how do we measure particles from tires? Because you can measure particles from tires in many environments, and this is really the real issue and a challenge decision, because depending on how you measure them, you will get a different result. Whether the environment is different, whether the surface road is different, you will get different results. If the driving conditions are different, you will get different results. So what does it mean, the tire emission? In fact, it means nothing if you don't take into consideration that you restrict all the other variables. So definition of how do you measure particles is fundamental. And you can measure particles in a realistic environment like real driving conditions, or in a proving ground where you have more controllable conditions, still really real in the sense that you are using the real environment, but you have less variables which are not controlled. But you can also measure particles, tire particles, in a laboratory using some type of roller or a special circle track where you control temperature, speed, angles of rotation. So in these conditions, you are somehow sacrificing representativity of the test, but you are getting a much more controllable environment. Still, you get very interesting results that allows you to understand better the process of generating particles. Now, there is the issue of correlation, how reality correlates with this test that you can perform in the lab. Well, this issue has also been addressed in this project. So this allows us to see how far you move from reality and what benefits you get from that and what drawbacks you get from this. Now, apart from this, then the next step is to propose standardized methods for tire abrasion rate and airborne particle emissions. So this will be a consequence of what we are really prepared to do. So from the first three steps, we will be able to propose a test that makes sense if what we want to make is a cost-effective test, or we want to make the best test that you can ever make. So this will be somehow a derivation of the first three activities that we have carried out. The next objective is to investigate the dispersion of the environmental fate of tire wear particles. So here in Leonti we have carried out an investigation using many field points in which we have acquired data from the soil, from the air, from the water around, and we can somehow, in some parts of Europe, we can map the particle number, the particle matter, the particle size distribution, and we have a broad idea how the particles disseminate, what the fate of these particles is, depending on where you are with respect to the sources and the road which is generating and accumulating these particles. So this gives us an idea how particles disseminate when they are produced by roads on, by tires rolling on a road, which is a fundamental part to be able to use in a reasonable way predictive models for dissemination. So this is a key point, to understand the initial steps of dissemination. This is fundamental. And when I say initial, I mean close to the source, but not extremely far from them. Okay? So this is something that has also been investigated. Another issue is to investigate the effect of tire noise, and now I move into the noise of tires. So I leave the issue of particles. Now we move into the noise, which is another pollutant. We have also investigated the characteristics of tire noise using about 25 samples of tire. We have extracted the fundamental structure of tire sound, and from that we have synthesized sounds which are artificial, but they take the fundamental components, like in a cook recipe, of tire noise. And we have exposed people to these samples, sleeping people, and we have measured the reaction and how we affect the sleeping qualities when they are exposed to these different tire sounds. And we will show you later that some of these sounds are somehow upsetting the cardiovascular balance of people when they sleep. So there is a trend of people that are exposed to these sounds that they can accumulate some damage and eventually generate or have some cardiovascular impact due to this interruption or deterioration of the quality of the sleep. Another interesting point of this project is that we have proposed a concept. It's just one concept of an airless tire, and a tire without air cavity. And there are many in the market. There are many proposals also in the media. But we have proposed another concept in which we have a tire with flexible spokes. And this is very much, let's say, like a panel, a rolling panel, in which the air can cross from both sides, which means that the panel does not vibrate, or at least if it vibrates, it will not pump air, so the noise will be reduced. And this is something that at the moment we have been used to develop a concept to build a first prototype that at the moment we are testing. I will show you this later. Another important point is now we are also in the process of recollecting the first the first values of contributions of tire generation by tires, and using them to provide some input of how we can use these values to predict the contamination or the pollution produced by tires in the environment. So another important topic or issue here is the consortium, which is made up by Audi, Ford, GRC in Brussels, VTI and TNO in Netherlands, VTI in Sweden, TNO and RIVM in Netherlands, UGOT in University of Gothenburg, Insights in Leon, VAX is an international consultancy company, ETU is a Swedish company that have developed the wheel, the LS tire, and Linlong in China. LLG is Linlong in China, which is another partner. This is an image. This is an image that tries to explain the transversality of the project. So you go from, let's see, oh yeah, so you go from the source to the final people that experience noise or experience toxicity, and what we are trying to understand is the source, the transfer of these particles or noise, and the receiver. And we are exploring basically all the 6 elements of this matrix. Results. Basically, this summarizes the results that so far we have produced in this point. Here, what you can see is a concept of how we can measure, as I was saying before, how we can measure particles in a driving vehicle, in an operational vehicle with a portable system in which we have installed equipment here at the back of the van and using an enclosure so that we can capture the particles generated by a tire rolling on the surface. So here we're sucking samples of air with some reduction in pressure and producing an analysis of the particles. At the moment, we're still developing this concept because, as you can imagine, this is not a closed box, it's an open box, and therefore what we are finding is that this leakage between the box and the road surface is producing many problems, so we're still working on that. But what we have done, and with good and some coherent results, is the test below using a heavy vehicle, is a swap body, Class C swap body truck, as a MAN TGX long distance truck, in which we have installed at the front and at the rear part wheels, axles, we have installed two probes to extract some sample of air with particles very close to the tires. And we are at the moment capable of producing this type of graphs, where you can see, for example, in the horizontal axis, the particle size. In the vertical axis here is the mass distribution, and here is the size distribution that we can measure at the front and the rear axle. And this has been done for many trucks, many driving conditions, in realistic conditions. And what you can see here clearly is that the driving behavior and the driving conditions, the amount of straight lines, the amount of turns, the speed, acceleration that you use for this circuit, produce really a change in these tracks, in these graphs. So what we see, sorry? Yes, so we see that at the moment, then this is really affecting the results. It's how you drive the vehicle and produce these measurements. The same has been done in a lab, and what we see at the moment is doing this type of test in the lab. Here we have a picture. We get this type of conclusions. Softer tires generate higher PM for both tires and roads. Winter tires, which tested yield tire wear particles higher amounts than summer and four-season tires, and the reason is because the softer the tire, the more particles they produce. The contribution of rubber wear to PM10 produced is between 1 and 5. This has been assessed here in this lab. So this is an important parameter that gives you the amount of PM from tire wear. And also important issues has been confirmed that the asphalt surface has an important influence on emission rate and particle size distribution. We find a bimodal size distribution with peaks at between 5 and 25 micrometers and between 50 and 200 micrometers. Right. This is the prototype that we have built. You can see the concept of this airless tire is produced or made with steel spokes, which are flexible, and at the moment it is working correctly, but we're still refining the prototype to make rolling resistance and noise tests. The noise effects. What we have found is the noise produced by airless tires produces less disturbance of sleep, which is good news if we can develop this wheel and prove the concept. Here we have used a simulation of the noise produced by an airless tire. What we will do at the end is to check that this simulation is consistent with the noise produced by the prototype that we are making. Also, the main reason of that seems to be related to the fact that for the same decibel level, which is, you know that the legislation takes into account dB level, but doesn't take into account loudness, which is a psychoacoustic parameter. What we see is that for the same decibel level, the airless tire has less loudness. Our loudness is associated with the subjective perception of disturbance. So what we see here is that this particular prototype produces less loudness, which can justify why we are getting better sleeping results, disturbance results with the airless tire. In terms of the emission factors, what we have done is to review 300 tire measurements in the past, and we have a proposal for C1 tires and for C2 and C3 tires of about 110 milligrams per kilometer. And the PM10, PM2.5 and particle number are of the order of 2.5% of the abrasion rate. PM2.5 is of the order of 40% of PM10, and particle number is of the order of 1 times 10 to the 10th. So these are values that we are proposing at the moment. Well, mitigation measures. So what is clear at the moment is that we can act to mitigate the generation of particles. We can act on the tires, but we can act also on the road surface, and we can act on anything that is taking or collecting these particles once they are produced. Whether should we are, I mean, as we act here, very close to the source, we will control better the generation of particles. But of course, we can always use reducing exposure and treatment particles by treating the runoff waters, street cleaning, and particle planting vegetation, which can somehow reduce the influence on people, but is less effective. And the last is this one. Other impacts which are important. We are working with, collaborating with nPETS and ULTRHAS in sharing information so that they can make better predictions of the impact of tire particles in the environment and on health. We are also discussing with DG GROW possible particle emissions scenarios and run sensibility analysis for abrasion rate and particle mass and particle numbers. Cost-benefit analysis for various particle emission scenarios will be considered in the project. We are also providing an example of the effect of a design of an airless tire, which is the one that you have seen, on tire noise. This is something that we will prove at the end of the project because we are still preparing the vehicle for a final noise test. And we confirm a new tire noise aspect causing impact on health, which is basically loudness, which goes beyond the decibel. Thank you very much.
Thank you very much. Since we are a couple of minutes beyond, if there's just one question. Okay, not. So,
Okay, thank you.
Fine for me. Thank you. So, we now move to ULTRHAS, which is one of the projects looking more in detail on the health impact. But as you can see from the opening slide, is one of those where is a wide angle, let's say, approach on the transport emissions sources. Sorry. And it's Mr. Jorevik, I don't know if I'm pronouncing the right, that is introducing this to us. Thank you very much.
Okay, thank you very much, and thank you for having the opportunity to come here and present some of our data. So this is the ULTRHAS project, Ultrafine Particles from Transportation, Health Assessment of Sources. And we are working under the same call as the nPETS and VMT projects, but under the subtopics as nPETS. Shortly about the project, it's coordinating from my institute, Norwegian Institute of Public Health. We have in total 7 partners. We started in beginning of September 21, and we will be running until throughout August 25. So we have still a lot of work left in the project. Yeah, due to time, I'll skip directly to this. As the nPETS project, there's a lot of things we do here. We do method development, standardization of protocols, and all of that. But since we only have 15 minutes today, I will try to sort of boil down to some of the key points that we try to address. And there's particularly 2 very important questions that we are concerned about. First of all is whether we actually can rank health hazards of different transport sources and explain or predict effects based on physical and chemical characteristics of the emissions. So it's, for instance, the ship emissions, are they more harmful than emissions from airplanes or from passenger cars? And can we, based on what we do in this and other projects, start predicting toxicity of emissions from other sources as well, so beyond what we're testing in the project? The other thing that we really need to determine is whether we actually need regulation of ultrafine particles. This has been on the agenda for many, many years now, and we still haven't got to the point where we have exposure limits for ultrafines. We do have limits for emissions from different sources, but for air quality, we still don't have a formal regulation of ultrafines. So a key question is whether we need regulation or whether effects are actually sufficiently captured by the current PM2.5 regulation. And to understand this, we need to dive into what is driving toxicity of particles. Is it the particle numbers? Is it the particle surface area? How much does particle chemistry mean? Is mass a good metric? So this is what we use currently. And for all of this, we are assessing effects both of the primary emissions and from secondary aerosols formed by aerosol atmospheric processes. In contrast to the nPETS project, who does a lot of field work, the ULTRHAS project is strictly based on laboratory studies under controlled conditions. And we are building the work around 3 major testing campaigns. The first one is on high power engines, so ship and jet emissions. This was done last winter at the University of Rostock. Non-exhaust emission sources like brake wear and rail catenary emissions, which is almost done. And actually today we started the last large campaign on exhaust emissions from light-duty vehicles. It's now running in Kuopio, where we will test gasoline, diesel, and natural gas cars. And for both the testing of exhaust emissions, we do fresh and also catalytic aged emissions. So we have the atmospheric aging process including to cover also secondary aerosols. And then we do testing in vitro models. So we have advanced cell models for the lung and for secondary organs, which we run in all campaigns. And we also do some limited animal experiments to validate those findings. In addition, we have a sort of 5th campaign which is more mechanistically based, where we do more model particles to tweak with chemistry and to understand more how the differences we see from the main campaign contribute to explain biological effects. So I'll go through some of the data we have from the high power engine campaign from last year. This is from the test facility in Rostock. We have a downscaled jet combustor to mimic emissions from a jet engine. A full-size jet would have blown the whole budget very fast. We're running this for 4 hours over many days. It will also have blown away all test equipment that we're trying to connect to it. But the University of Bundeswehr has a small jet combustor which we have used, and that's been running on JP jet fuel. Then we have a marine engine running on marine gas oil and also heavy fuel oil. So marine gas oil is low in sulfur, so it's sort of a requirement for European harbors and SECA zones, so where you have sulfur controlled zones like the Baltic Sea. And heavy fuel oil, which is higher in sulfur and which can be used in the Atlantics and in the Mediterranean. And here is the whole part, or at least part of the test area. And within here we have the cell facility, which we have moved into the engine unit at the University of Rostock. And we do direct exposures of cells under air liquid interface. So it's yeah. Okay, so this figure shows you the size distribution of particles. So on top we have the emissions from the jet combustor rig, then we have the marine engine with marine gas oil, and the marine engine with heavy fuel oil on the bottom. And on the left we have the fresh emissions, and on the right we have the aged emissions, and then it's particle number, concentrations, and size on the x-axis. And as you can see, for all particles or all emissions, there's a number of particles in the smaller range of nano size, so well below the 100 nanometers for the fresh emissions, specifically for the jet combustor rig and for the heavy fuel oils running on a low engine load. You see there's a high number of small particles around 20-25 nanometers. When we do aging, there's a significant shift to the right. We get larger particles, we get more particle mass, and we get higher particle numbers, so all parameters are increasing. and they're increasing quite comprehensively. You can see, especially for the jet combustion rig, you can see the difference on the scale here, 2.5 and 8. We have done or estimated emission factors for this. For the jet fuel emissions, you can see that the primary emissions are relatively low, 0.09 grams per kilo fuel burnt, almost 30 times higher for the marine gas oil, and even threefold higher than that for the heavy fuel oil. So there's a marked increase in particle emissions in mass from the primary emissions from the jet fuel to the MGO to the heavy fuel oil. However, if you look on the secondary aerosols, the jet fuel really produces a large amount of emissions, a large amount of mass. If we're looking into particle number concentrations, again, the jet fuel producing a lot of small particles also has much more particles than the others, especially considerably more than the marine gas oil. There's actually quite a lot also for heavy fuel oil in the small size range. And again, when you age, it's almost a 10-fold increase in particle emissions, in particle number concentration. So both mass and number goes up from the photocatalytical processes. This figure shows some of the coarse chemical characterization of the particles. In black, you can see black carbon. And then we have in the green, you have organic chemicals, and yellow is sulfur. And then there's some nitrogen compounds. But on the left here, you can see the fresh particles. For the jet engine, we run a stable, set, fixed load, because we cannot change it because of the power it sort of shoots into the testing system and the cells. For the marine engine, we have different loads, and you can see how load actually affects primary emissions quite significantly. So low engine loads, which you would expect to have in a harbor, is what actually produces most. There's also much more emissions from the heavy fuel oil. And then we have the aging, and please mind the difference on the scale. So if you want to compare this directly, this is actually how it relates from the fresh to the aged. And you can see that for the jet fuel, there is this massive increase in organic chemicals, which condense onto primary particles. And basically, it's a lot of aliphatic hydrocarbons from unburned fuel, which is vaporized during the emission, and then when it cools down, it builds these large particles. And you also see that for the marine gas engine emissions, there is a marked increase. Especially the heavy fuel oils contains a lot of polycyclic aromatic hydrocarbons, but after photochemical aging, they're almost completely broken down. So a lot of oxidized species. For toxicity, I've always showed some of the data from the jet combustion emissions. There is at the doses we are exposing, there is no direct cytotoxicity to the cells, so the cells are not dying at these exposure levels. There is also no effect on the transepithelial resistance, which means that the integrity of the barrier, the alveolar or the lung barrier, is intact. But we see, especially for fresh emissions, there's a marked increase in oxidation products. So this is malone dialdehyde, which is a lipid peroxidation product. So it means that there's an oxidant process going on. There's also effects from the secondary emissions, but much less than we see with the primary emissions. This is a nice picture. I can just leave it for itself, and it probably speaks by itself. No, this is quite messy. What it is a huge amount of different pro-inflammatory proteins, and we're interested in inflammation because it's considered one of the driving factors of adverse effects from air pollution. And we have both the fresh and the aged ones here, and what we see is that different dilutions and aging and fresh are inducing effects. There are differences in the magnitude of responses, but there is also qualitative shifts, which makes it a bit more difficult to predict what is actually going on from sort of a risk point of view. It's not just that a certain response is stronger or low or weaker, but there's actually a shift in the type of responses. So we need more time to understand what this means, and we need to validate more of these findings. We do a lot on gene expression and RNA-seq, so we will have more data in not too long to sort of underpin this. So what conclusions can we draw so far? We should be careful. We are still almost in the middle of the project, so there's a lot more data coming out, but at least atmospheric aging seems to be very important. It increases particle size, it increases particle mass, and it increases number concentrations. This is not happy, so we probably have a question, but at least this is what we measure. There is this qualitative shift in toxicity, which is always difficult to sort of interpret in terms of what it means to health, and it warrants more studies. But what we see so far is that particle chemistry is important, and I think that's also some of the same thing that I see in the nPETS project. And it's important, especially for the organic chemicals, and it's important to consider that a lot of this is due to volatiles that are emitted and which condensate on particles in the end. And if you go out in the real life, a lot of the organics will be found in the larger fractions and not necessarily within the ultrafines. So we need also to not only consider ultrafine particles, but also the volatiles and semi-volatile emissions. Impacts. So we hope to produce, or we're trying to produce, novel insight into the mechanism and key drivers of adverse effects from transport emissions, and evaluate the roles of the ultrafine particles, including the extremely fine ones below 23 and 10 nanometers, the importance of particle mass versus particle size and number concentrations, the chemical composition, specific emission sources, and the role of the atmospheric processes. We also develop and validate in vitro cell-based assays for toxicity testing and risk assessment of air pollution to complement current epidemiology-based approaches. Yes, almost there. Because the problem with epidemiology is that it's difficult to get the resolution necessary to actually understand the impact of individual sources and individual components. And in the wider impact, we have to provide guidance for developing and prioritizing mitigation measures in future legislation of air pollution and air quality, rank health hazards of transport modes, determine need for UFP regulation, especially the really small ones, and determine the need for regulation of VOCs and SWOC emissions, especially focusing on secondary particle precursors, and hopefully contribute towards the Zero Pollution Action Plan and the need to reduce the health impact from emissions. And as already mentioned, we are collaborating well across the three projects. We are discussing joint sharing of data. We have joint workshops. We had one on emission factors this autumn. We will have a new workshop now in March on biological effects, and we will have a later workshop also on policy development. And yeah, thank you.
Thank you for keeping almost perfectly the time. Is there any detailed question on the content? Yes, please. This is.
Just a question. How did you explain this very big increase in particle number with aging? Because it is counterintuitive, and some of the explanations, even the figure you gave, shows exactly the opposite. The figure, I mean, the simple.
So I think I'm not completely sure. I'm a toxicologist, so there's others in the consortium which are the expert on the aerosol side. But I mean, a lot of this could also be related to really small primary particles, which we perhaps are not capturing well enough. It could be one which, and as they grow, they will be more easy to measure. That could be an artifact. I'm not sure. I think that the really tricky question is why size or the number concentration increase. I mean, it makes sense that it's stable. Not necessarily, unless you get aggregates, then you will expect a decrease. But from what we measured so far, it's increased actually. But it's not. This is a simplified point. If you see here for the, I mean, it's quite straightforward with the jet combustor. But for the marine gas emissions, you see that there's this biphasic, and actually what happens is is that these two phases are sort of covered probably by this larger peak that sort of dominates everything, and which is actually in the middle for some reason.
Maybe one question is it ends close to 10. Where is the lowest you can measure? Because we have seen in other projects that sometimes you have 1 or 2 nanometers. If you're not measuring, those could be the ones that become visible when they grow.
We are measuring below 10. I don't recall how good the measurement is. Yeah, 7-ish. And I'm not sure how the uncertainty is when you really get below. But certainly, I mean, if you have things below 7, if you have things down to really a few nanometers, which we are not measuring, that could be an explanation for moving. So as those functions
and they become visible
for the VOCs, and then suddenly they pop up.
Yeah.
So yeah.
Thank you. Any other question of clarification? No? Okay. Then thank you very much for the presentation and the answers. And we move to Dr. Lehmann from Aerosol FD, who's looking at retrofits, as I mentioned in the introduction, but also here in a wide area, so some different modes and different applications. The floor is yours.
Thank you for the kind introduction. Welcome to this talk about AeroSolfd. AeroSolvd is not a typo, it's an abbreviation of an interesting project. It's a fast track to cleaner, healthier urban aerosols by market-ready solutions for retrofit filtration devices for tailpipe, brake, and closed environment. So what are we addressing? We are addressing the innovation action for development and demonstration of cost-affordable and adaptable retrofit solutions for tailpipe and brake polluting emissions. How do we do that? We have put a consortium together covering Europe, working on retrofit solutions through reduced tailpipe emissions. We will develop a filter for that in the exhaust. We will develop reduced brake emissions. For that, we develop a brake dust particle filter, and we look at pollutions at metro stations. There will be a filter that can be deployed at these stations. The budget is 5 million from the EU. We are lucky to get 2.2 million from Switzerland, and the industry in the innovation action is giving 1 million, and the project is running from May 2022 until April 2025. What are the partners that we put together to do the work? We are doing first measurements, looking at what the emissions are of the cars at the locations in the metro. IDIADA is working on that, and Cardiff in Spain. Link is doing the measurements of the brake, and Utah is helping them with the particle emissions. We also assess what the effect is. We do a social environmental analysis. Cenex is helping us with that. We have the Workers' Health Department in Denmark working on that, NFA, and social science, citizen science plays a role, so Intec in Portugal is supporting that. Very important are our demo sites. So we are collaborating with bus operating companies in Ljubljana, LPP, in Ancona, Italy, and in Spain, Auvaza in Valladolid, and the city is helping and supporting with the Innovation Center a great relationship. For the metro, we have Metro Lisbon, and we have a site in Sofia where we are doing the installation and testing. All that, dissemination, combination, exploitation, and management, and so on, we have a great support by Steinbeis and working together as a team on this project. So how far have we come? What have we done in the project so far where we are? Looking at the results at the end, we want to go to an environmental social life cycle assessment. We need that one because we want to bring the products to the market. If there is no incentive, regulations would be great, but perhaps it will sell even with an ESG that could help and bring the products to the market. For the tailpipe, we are focusing on gasoline fleets before Euro 6C and earlier. We have identified 4 vehicle engine types. We have validated and measured in detail 4 vehicles. We have looked at the secondary emissions. We have 50 vehicles to monitor the performance of the retrofit solutions, and we will measure 1,000 vehicles to check the compliance. We have currently measured 300. For the brake dust particle filter, we have looked at how can we measure brake emissions? How can they be evaluated? What is the emissions in a city? So we have come up with a method to define an urban cycle for buses. We are now going to put that on a dynamometer to measure the emissions. In the meantime, we have developed a brake dust particle filter and done the virtual assessment simulations. Prototypes are done. This will now go on a car, on a truck, to be evaluated on road and tested in winter conditions. And most important, we have started defining a type approval process, because to sell the products later, they need to be a type approval. For the metro stations, we have identified how we can trace the brake emissions to the air particles that are in the air. We will measure that in Lisbon and in Sofia, currently preparing the setup for Lisbon. We will have optimized our air filters to be ready and installed there, vandalism protection, for example, and we will demonstrate also in a restricted area how air filters can improve air quality in a semi-closed environment, and later we will define a best practice. What are the results so far? Looking at the tailpipe retrofit filters, we have identified the vehicles, and you can see the list here. These are vehicles we are looking at: Opel Corsa, Peugeot 508, 5008, VW Golf, and so on. These are the vehicles. The retrofit solutions have been designed to fit into the exhaust path, and then we have tested 4 vehicles in detail to look how they comply, and we have seen, to see the results in the table, 1 vehicle that didn't comply, and we stopped that testing. And what we do, a solution here is we replace it with the original 3-way catalyst, and by that we are compliant again. We are doing the field test. 330 vehicles are currently in the test. We need more vehicles, so if you have a vehicle that fits into that range and that we can test, please sign up. Loretta is sitting here in the room, and from Word, our partner, and please let her know if you have a vehicle that can fit to that. For the brake dust filter, we have looked at our partner cities. How are the buses driving? What is the topography? Where are they going? We have identified routes. We have put instruments on the buses to track the brake events, and this is now translated into a brake cycle for the city, specific for one city. We have done that for Valladolid. We have done that for Ancona. For Ljubljana, we are still waiting, because we want to see the difference between a hybrid bus and an ICE bus, and we are currently looking how we can get the canvas data, but we are on a good path to get that soon. And in the meantime, we have designed the brake dust particle filter. You can see the prototype that's tested now, and it fits on a ZF air disc brake. For the metro was in the other talks as well. We are going for installing filters. You can see an augmented reality picture where you can see the filter standing in a metro. That's where we looked to find a good spot over there, and we will also have the design optimized. But how to trace the particles? We did measurements of brake emissions of disc types from Metro Lisbon. We looked at a way where it's recuperation and friction, 50-50, so on, and then where brake emissions are only used below 10 kilometers per hour, because most is done by recuperation. But in both cases, we can see that antimony is a good tracer material, and the 200 nanometer particles are quite well to see if the emissions on the platform are coming from the brakes. So we will install them soon in Lisbon. There are some challenges getting them to the station, but this is exactly what we want to know in the project. How can we later do it better, and how we can come up with a good practice to get the filters on the platform. We also use the advantage that we have a bus depot. That's a public restricted area where we can install more measurement equipment, where we don't need to look for vandalism protection. We can have the low-cost sensors deployed across the hall, and we look at particle emissions indoor and outdoor. And you can see, if you look at the hours, that at 7 and 8 and 9, there's a higher particle concentration. That's when the buses are leaving the depot, and when they return later, there is again a slight peak, but they don't come at the same time as they leave, almost all at the same time. So we will do more studies on this area over there. Very important, as I said at the beginning, environmental social life cycle assessment of the retrofit parts. What is the real benefit for the society? The colleagues have established a framework, what data we need, how we are going to assess that the deliverable that you can find. What are the long-term expected impacts of the project?
Road traffic is dangerous, we know that, but the greatest danger it poses is tiny and completely underestimated. Correct, we are talking about traffic-related emissions. In other words, tiny particles released through the exhaust and wear of parts enter the air we breathe. This happens, for example, when braking, while rolling and burning fuel. In semi-open enclosed environments like underground stations and tunnels, the effect is particularly bad. Retrofits are transition technologies until the full electrification of Europe's transport fleet. Even beyond, brake retrofits play an important role in the electrified fleet. AeroSolvd is an EU co-funded project that aims to deliver affordable, adaptable, and environmentally friendly retrofit solutions to reduce traffic-related air pollution. Eliminating the harmful effects of ultrafine particle emissions from engine combustion on health and the environment is urgently needed in the transition towards cleaner mobility. In AeroSolvd project, we develop and demonstrate a cost-efficient tailpipe particle filter for the European gasoline fleet segment, which currently drives without any exhaust filter technology. This retrofit solution can replace the underfloor silencer, but is less noisy than the original vehicle and eliminates the number of solid ultrafine particles emitted. Brake dust is also considered particularly toxic. Not only vehicles but also buses and trains emit large amounts of emissions from brakes, tires, and rail wheel contact. Therefore, we will modify an existing and proven passive brake dust particle filter concept for passenger vehicles for bus and commercial vehicle brake applications. This solution, which is specially designed for long-lived public road transport assets like buses, will reduce brake emissions and capture brake dust at the source. Fine particles in semi-closed spaces like metro stations and bus stops pose a threat to human health. To tackle these challenges, we will provide an effective stationary air purifier that captures particulate matter from the environment and safely trap it in the filter, reducing exposure for public transit passengers and workers. In AeroSolvd, our aim is to offer sustainable solutions with substantial social benefits achieved through an overall sustainability assessment focusing on the environment, health, and social dimensions. Get to know more and visit our website.
So to summarize, we will demonstrate the retrofit solutions for the tailpipe to reduce the emissions in the field so that later you don't need a new car to have better urban air quality. We will also define a brake dust cycle. We have done that already, a way to come up with a brake dust cycle for the cities. We will come up with a type approval at the end of the project. The air purifiers will be demonstrated, and we have a framework to assess the overall environmental and social LCA. And there will be collaboration with others like the Ideal Cluster of Hadea, where we do an assessment of air quality at metro stations, a workshop in Barcelona. The save the date is out. Happy to see you in Barcelona on May 23rd. So all in all, a great team. Thank you for your listening here to the talk, and please follow us on LinkedIn to get the numbers higher and to get the very interesting news of this project. Thank you very much.
Thank you very much also for being given in advance by a minute or so. Is there any question on the project? Yes, this is.
Thank you very much. Can you tell us a few words about the filtration technology you're employing? What type of filter is it? What type of material?
That depends on the
For the cars, I mean.
For the cars, for the particle filter, you can later talk to Loretta. She knows the details.
Yeah, maybe one question, because you also are working on tunnels and so on. So I'm just wondering, are you seeing results like the previous speaker, or maybe you are in a place where, I don't know, the filtration is worse or whatever? I mean, do you see, what levels do you see in the metro stations you're working on?
I would be happy to share that, but the measurements have not started yet.
Okay, well, in due time then. Thank you. Any more? Okay, well, thank you very much. So we are in a way going back in time, because here is the project that just finished. So we have the, let's say, the final view on what they've done in the project Tube. Pasijalava will talk about this project, which is looking into health impact, particularly on brain, but also somehow there is something on the lungs, and of course all the measurements that are needed for that. The floor is yours, please.
Thank you for the introduction, and thank you for the invitation here, and also thanks to the previous presenters, because it seems that we have been working with quite similar topics in many cases, and I hope that we can also later, although our project is ended, combine some of the efforts done. So, Tube, Transport Derived Ultrafines and the Brain Effects consortium was quite a large one, with over 5 million euros of European Union contribution. We had several universities from Finland, from the Netherlands, Sweden, from UK, Italy, Denmark, Germany, and some companies, also Mimetas, Biotalent Particle, and 10 research institutes in several countries also, including Finland and Netherlands and Czechia and Germany. And as this was an international collaboration project, we had also partners from China and Chile. And overall objectives were to study ultrafine particles in different environments, do research on their respiratory effects and genotoxicity, effects on the brain, particularly on Alzheimer's disease, and then study with animal models how the particles affect, ultrafine particles affect the clearance mechanisms from the brain, and how the harmful substances are removed from the brain. Then we had population studies included, both from Sweden and from China, and then finally we did risk assessment and studies on how we could reduce the most harmful exposures. And so we did measurements also in various different environments, including street canyons, residential areas, harbors, and vicinity of airport. Then we did a lot of measurements with different cars that are listed here. They are actually quite small here, but we had gasoline and gasoline with alkylate fuel, diesel car, and non-aromatic diesel fuel in that, and then we had the natural gas powered car. And as the aromatic content of the fuel was also one of the points in the call that was answered, this was one of the major findings that by reducing the aromatic content in diesel fuel or in gasoline fuel, we can then reduce the emissions and also their harmfulness. We found that there are really large variation in different environments. For example, it's surprising how much vicinity of airport can affect the concentrations of ultrafine particles. And as in the previous presentation also, we found ultrafine particles in all the measurement locations. from this car campaign, it was important that we measured very small nanoparticles down to even less than 1.2 nanometer particles, and there were a lot of these particles in many cases. Gas-powered car is considered to be quite clean, but after because it doesn't have any particulate filtration technology included, it emits a large quantity of very small particles. And also the gasoline-powered car is emitting a lot of particles if it's not equipped with gasoline particle filter. And in our studies, we showed that these particle filtration technologies, both in gasoline and diesel cars, are very efficient in reducing the emissions. We then obviously did also different types of toxicity measurements with particles from these cars. We saw that there are certain cars that are causing more effects than the others, and also the operating temperature affects quite a lot actually these emissions. And this could be one point that could be included in future in also regulations, that how the cars are operating in different environmental conditions. And one interesting finding also, as a side note from these respiratory effects, was observed that ultrafine particles, the concentrations during the pregnancy may modify the air pollution exposure later into life. But this is of course mouse study and cannot directly extrapolate it to human. And then of course we did a lot of research on brain effects with several approaches, including olfactory models. We had brain organoid models, and then we had mouse studies. It was observed that the ultrafine particles disturbed the mechanisms that are leading to removal of harmful substances from the brain. In olfactory cultures, it was obvious that emissions from higher aromatic fuel emissions, exhaust emissions, caused larger effects. For example, here in this picture here, we have differently expressed genes. A20 is diesel fuel with aromatic content of 20%. A0 is hydrotreated vegetable oil with basically no aromatics in the fuel. This is from heavy duty and unfiltered. And then finally we had Euro 6D diesel car operated also with A0 fuel. And as you can see, this aromatic content of fuel quite largely activated more genes than non-aromatic fuel, and then again in the newest diesel vehicle there were basically no activation for anything, which shows that these studies or the regulations have been working towards cleaner exhaust. In population studies, there were quite limited findings because usually the ultrafine particles are not measured. And this was also mentioned in one of the previous presentations, that we should have a better resolution for ultrafine particle measurements in the environment, that we could reliably do also epidemiological studies on these these particles. We had also a study with healthy volunteers, and it was observed that when they were exposed to diesel exhaust, the odor threshold value was increased, and this is actually one of the early indicators of Alzheimer's disease. And interestingly, this was seen in women, but not in men, indicating that there are sex-related differences in these effects also. And then finally, we had risk assessment, and because some of the drawbacks in the data, we couldn't develop adverse outcome pathways from the project data, but anyhow, this adds to knowledge on other information from the ultrafine particles. The problem that was also asked and mentioned before is the dose response in ALI systems, because we were using a lot of ALI systems in the in the project. Usually the dose is then fixed according to dilution, and we cannot do the traditional dose response that is done, for example, with the collected particles. And actually, when we were working with very clean cars, we had to reinvent also the dose, and instead of mass-based dose, which is almost non-existing, we used emission volume-based dosing, which worked out quite well in the project. And we were also able to suggest some strategies to reduce traffic-related pollutants and their harmful effects, and they are listed in two last slides. And we also recognized some gaps of knowledge, and particle emission regulations should be developed to reduce especially the ultrafine particles in urban areas. Those can be from various different sources, and important would be gain also information on the concentrations of these particles in different locations and different emission environments, because by doing that, we could also better do the population studies with ultrafine particles. Also in our project, the semi-volatile compounds derived from the exhaust seem to be contributing to secondary particle formation, which should be also considered in future emission standards and measurement methods. And all in all, more effort should be put on characterization of semi-volatile ultrafine particle health hazards, including the better characterization of the compounds. We, as a project, recommend decreasing aromatic content of the fuels, which would reduce emissions rapidly, also the current fleet. A large variation in fuel properties impacts the specific conditions, such as the cold start should be also included. We studied mostly acute or subchronic effects, but it's likely that neurotoxic effects and diseases are seen better in prolonged exposures, even though we saw quite clear evidence on the harmfulness of ultrafine particles. And the future investigations should also be focusing on ultrafine particle measurement containing also the very smallest particles, which is one of the knowledge gap of the measurements. And also, it would be nice to have more information on different emission environments, as I mentioned before. And by this, I'd like to thank you for listening, and if you have any questions, I'm happy to answer.
Yeah, thank you very much. For treating everything, every presentation the same, one immediate question for understanding before we enter the real Q&A. Is there one question?
Thanks. I really appreciated your recommendations. That was good. Going back to the first one, because I think the first one is actually mentioned biofuels. So I guess my question is biofuels, did I understand correctly, will reduce particulate emissions, but also going back to the fuels, how much variation do we actually see already in that space?
Well, I have to also answer that I'm a toxicologist, but I try to answer this. Yeah, of course, there is a variation in fuels that we are calling biofuels. We did all the tests with this hydrotreated vegetable oil, which can be used as a normal diesel fuel. But then there are also, depending on the market area, there are biofuels like methyl ester fuels that cannot be mixed in high concentrations to regular diesel fuel. And I would say that these really have a big difference also for the engine operations and effects. But that was not included in the project because at least we believe that this next generation biofuel is much better for the emissions and for the vehicles themselves.
Okay, so then thank you very much. And before we start the Q&A, let me wrap up shortly in my words what we have heard. So we have heard and seen results from 5 projects about particles, noise, and the impacts on health, etc. Which is for us in the road transport sector especially relevant since we are moving towards electric mobility. So tailpipe emissions will not be a topic in the future, but is current to be addressed. And we have learned about the creation and the fate of particles, the life of particles, growing, multiplying, etc. The sources of particles, and we have learned about approaches to understand all this topic, to understand more about the health impacts with new methods that have been applied. We have also seen steps towards standardization, towards databases that could be used for future regulations on standards. We have also seen solutions, innovations that could be applied very soon, real hardware prototypes for like the airless tire, like dust and filter capture systems for the brake dust, for example. And overall, we have lots of results looking into the future, but we have also solutions and thoughts about the current fleet. So we are opening the whole time frame from now into the future. And since we have kind of covered the whole system, I would open up the Q&A and yeah, invite you to place your questions. And maybe please state your name and entity that you are coming from.
Hello,
First, thanks to all of you. It was quite interesting, I would say. My question for the whole panelists would be, how do we collectively reduce emission particles? And collectively, I would say user, fleet managers, OEMs, industrials, and so on and so forth. We have seen a lot of potential technologies to reduce particle emissions in number, but also in toxicology. And how do we rank the urgency, I would say? Do we start working on the braking scenarios, tire and braking systems improvement, material improvements, and so on? Do we work on the road surfaces? What are the most prescient matters, I would say?
Someone who wants to take over?
I can give it a go. I think it's a difficult question, but with the transition we now have into electric vehicles, I think one of the sort of main things that we need to consider is whether the health effects that we know derived from air pollution today, a lot of that has been linked to traffic. Is it the combustion emissions or is it the other ones? I think sort of clarifying that issue, because the combustion emissions will be going down. They have been going down with improved cleansing systems, and they will be going further down as we get more and more electric vehicles. There's still probably some heavy-duty engines in there, but for me, that is one of the big questions. Are these other particles really inducing the same types of effects? What we know from studies going back to the 60s and 70s on smoking, which is also a combustion particle exposure, the organic chemicals are rapidly detaching and going into the bloodstream, and they're inducing a lot of the same effects that we see from air pollution. Although different dose, there's a nicotine in, but we see it with workers exposed to polycyclic aromatic hydrocarbons. They get cardiovascular disease and so forth. So there's a lot of studies that point to the organic fractions as very important for at least some of the health effects. But we don't know whether that's all. We don't know what the accumulation of metal nanoparticles, for instance, in the brain would do over time, but I think this is one of the key issues that we should clarify, because it would be important to understand what we need in the future in terms of regulating the non-exhaust emissions. Not sure if it actually answers your question, but at least a starting point, I guess. We are treating all particles today as equally toxic in terms of regulation, but from the tox labs we know that they really induce a lot of different effects. And from epidemiology we know that quartz and asbestos exposures do give different effects than outdoor air pollution. So,
Well,
Still
then
an
we
answer?
go on this question and then we ask for
If I may add, I'm not a toxicologist, I'm not an epidemiologist, but I think at the end we want better air. So what solutions do we bring better to the market? Where are the early adapters? Who is willing to invest, or what city is willing to do something to have a solution applied? I think that's more important than thinking what are the best solution and what's the technology. Get us moving, get us doing something.
If I may add one thing, I think we have all these factors, but one thing that came from Leonti is that those particles are something like 1/100th of the other ones. So in giving a ranking, maybe it tells us, okay, tire particles, not so important, because it's a minute fraction of the total numbers anyway. And then the other point is if there are significant differences. We've seen the airport numbers. I think airports have not been in the picture for a long time, while we see that what they put into the environment, even if then it moves a little bit, but still is huge numbers, and secondary as well. When you combine the two, you showed numbers which are really awful. So when we are talking about big order of magnitudes, something like which is 100 times or something which is 100ths or something like that, I think that can also give some ideas.
Okay, maybe I'll play devil's advocate Steve Phillips, Conference European Directors Road. I just want to react to the comment was there and actually reinforce the last recommendation we saw on the table, because we are bombarded day to day with these comments from, quote from the World Health Organization about how many people die from air quality related issues. And you have to drill down to actually find the clarification of how much as that it actually is related to road transport. And I think we've underlined today, actually maybe we don't even know how much is related to road transport. So I do think there is a really important need here. I mean, we hear, recently we've heard a lot about the impacts of the wildfires, particularly from North America. So there's now a lot of area there looking at other sources. We are also see things coming about, the amount of air pollution you're exposed to in your kitchen from domestic cooking and things like that. So what I'm saying is, I'm playing devil's advocate because I'm saying let's stop making road transport always the baddie. But on the other hand, I recognise that there are things we can do within the road transport sector, to answer the gentleman's question, too, and I think we've heard some good examples today. So let's not always demonise roads, but let's contribute to part of the solution. Just a sturdy example.
That was a statement.
I was inviting them to comment.
Yes, please.
Well, I agree to a certain extent. I mean, when probably road traffic is where we had the biggest improvement. In Norway these days, it's wood fire that really gives the high numbers. Now, a few weeks back, we had a really cold period, and pollution level in Oslo skyrocketed. Really, really bad quality because of inversion, and then it comes up. It peaks at night at around 8 to 9 after the major traffic is gone, and people are starting to fire up their wood stoves. Then you have that problem. So I think we've been really good in terms of improving emissions from road traffic. And you saw the curves here from Stockholm, how particle number concentration has been going down. So the Euro system has been a great success. But we should also keep in mind that we have strong epidemiological data showing that proximity to traffic roads is not good for you. So there are something there. It's not to say that it's still the same. I mean, it's probably much better today.
Not causation.
I agree. Yeah.
There are results showing it. There are results showing, I mean, there's a study I remember where mouth cancer of people living in a road where there is traffic and working there was much higher than, so I think their proximity was playing.
I'd like to see the controls.
Hello, Peter York from the Flemish Government Department Mobility. I have a last question of the last about last presentation. There was said that in epidemiological studies, the relation between long-term air pollution and dementia was seen. Is there like a correlation, or is there already a clear statistically causal relationship?
Okay, in this study that was included in TUBE project, I think the connection was quite clear, but I'm actually not sure about the causality because the estimates were from PM2.5 and also nitrous oxide concentrations in the environment, and not specifically ultrafine particles, because they are not standardly measured, and this is why one of the recommendations was that we should have more measurements for ultrafine particles, also to increase the reliability to epidemiological studies. But the connection between the road traffic in this case was clear for Alzheimer's disease, and this is a kind of also finding, because it's from Sweden, having quite low air pollution concentrations, and even in those low concentrations, the effect was visible. And this is kind of one dilemma of pollution research also, that if we consider very clean environments compared to very polluted cities in, for example, in Asia, the dose response curves also in the people are completely different. So it seems that if we start from low concentration, it first the dose response curve increases rapidly, and then it will like smoothen towards the end. And one comment also to previous question, that well, why make a road traffic the body all the time? I wouldn't like to consider like that, because, for example, our results showed quite clearly that already what has been done in road traffic, for example, including different filtration methods, gasoline particle filter was decreasing, for example, very much these gasoline car emissions. So it's also finding the technological solutions, and not kind of only to blame the road traffic.
Yeah, but you show the problem is those who don't apply these technological solutions.
Yeah.
Thank you very much for this answer.
But I have a comment. I would like,
Go ahead.
Yes, I think, but I think that always what makes sense, if it's possible, is the control at source is always more effective. But the problem with the control at source in any type of engineering problem is that you really need a very good insight into the physical or chemical phenomena that you are controlling. But always the control at source is what really matters. In the field of tire particles, what really makes sense, and it's something that at the moment Euro 7 is not taking into account, is the pair surface, road surface and tire. It doesn't really make sense to say tire particles are not related with tires, are related with the interaction between tires and the corresponding surface. This makes a big difference. So what I want to say is that there is a lot of potential in understanding it is really a friction phenomena. So if you change the pattern, if you change the road surface, you will change dramatically the particles generated. So I think a lot more research is really necessary to understand the interaction for two reasons. One is because you control the generation of particles, but also because you have a potential source of trapping particles, which is the same surface. You can apply or understand or apply physical, chemical ideas to trap the particles on the road surface, and then use clean processes to control or to avoid the dissemination. So there is a lot of potential in understanding this mechanism of an interaction tire and road surface. And at the moment, this is not well understood. I know that it might be difficult to accept that, but this should be the cheapest action that you can take if you consider how expensive it is to apply mitigation actions later once the particles have disseminated. This is always the worst solution from an economic and efficiency point of view. This is my view of the situation.
Sorry, this is Maurizio Maggiore, University. I don't know if this works. It does.
Yeah, it was good.
I think this is a point that it worth a bit more attention. The fact that we're talking about tire particles, but actually we're talking about airborne tire particles so far. And there is always this important amount of particles that are not airborne. They're not measured. And they contribute to pollution at the same time, right? So you mentioned it. This is under microplastics, but I don't think, or maybe I missed this part of your presentation. Are you doing something in this area, or how you are addressing the issue of the, roughly speaking, 80% of particles that are not airborne?
Okay, we are assessing the dissemination of particles.
When you say dissemination, you mean Dispersion, I guess.
Dispersion on the soil, on the waters, on the sea, on the rivers of tire particles. So these particles can be very easily controlled if you do it at source, as soon as they are generated on the road surface.
On the road surface, and then
And
clean the road surface, and
well,
collect the particles.
From an intuitive point of view, the closer you are to the source, the easiest will be to control the generation. And if they generate immediately, you absorb them or you control them. This is very much like the noise concept. If you control the noise at source, you will get always more effective solutions. But it requires understanding always. In acoustics, always this is the case. But the problem is always more difficult to understand the physics to do that. But any action that you do on the source requires a better understanding of the physics. Once the noise has been produced and expands and propagates, it's too late. What are you going to do with the noise? The only thing you can do is to close yourself in a box and you will not listen to the sound. This is what you are trying to do with the particles, to put ourselves into a box and avoid the influence and the pollution and not breathing the particles.
Here, not talking about noise.
But it is the same phenomena. It is the same phenomena. Once it is spread, it is too late in cost efficiency terms. And this is my point of view.
Yeah,
Ulf, what do you think?
I totally agree that we have two surfaces in contact and we need them to interact. And I can say that I show a decreasing trend for the PM emission from my hometown Stockholm. But when we start to run 3,000 kilogram SUVs with started tires on the wheels that we need during the winter, then we will have an increase, for sure, at least according to our models. And we need the started tires to roughen the surfaces during the winter because they have adapted the road material. So they are too smooth if we don't run started tires during the winter season. We need them to have a rough enough surface to avoid too smooth surfaces during the summer period. So it's a balanced equation here.
So thank you very much for this lovely discussion. I'm sorry, I think we are over time already, but my recommendation is to move on afterwards, but I don't want to sacrifice your time for networking. So next agenda point is now the coffee break and further discussions, of course, and 4:30, the next parallel sessions will start. Thank you very much also to the speakers and your teams.